In the last video, I started reworking an old unreleased game from scratch, and here's what it looked like at the end of that. You could assign controllers to the players and move them around. You could also walk through walls because the players lacked collision, and so collision was the first thing I started working on after that. Now collisions are actually surprisingly easy to implement in Godot since it has built-in functions for that, so it only took a couple lines of code. But while we're on the topic of movement, right now we're directly controlling the player's speed with the movement input, which makes the player very responsive, but the lack of inertia just makes it feel a little off, since in real life anything with mass has inertia. So instead of directly controlling the speed, we'll control a new variable called acceleration and add that to the speed every frame. This means that the speed can only change a certain amount every frame, which simulates inertia. Now this already feels a lot better than before, but we still need something that slows the player down, since if the acceleration is 0, the speed will just remain the same. Now what games would normally do is add a little bit of friction every frame to slow down the movement, and the friction is just a small but constant force that goes towards 0 movement. But what I'm gonna do here is not at all conventional. You see, I'm only gonna add the friction when acceleration is 0, and that has some interesting effects on the movement. For demonstration, here's how the movement is done usually, which is adding friction every frame. Now this works fine in most cases, but there is an issue when the movement interacts with collision. Here you can see the movement input broken down to its x and y values, red and green respectively. And when we move towards a wall, one of these values gets nullified, making the player slower than it normally would be. Now this is actually fairly intuitive and realistic, and so it fits most games. But in this game, being able to move fast is imperative to winning or losing. So my solution, which is only applying friction when there's no movement input, means that you can still build up momentum while running towards a wall and go at full speed. Now this does feel weird at first since it's not at all a conventional thing to do, but it makes the movement and subsequently the entire gameplay so much smoother when every corner isn't out to get you. It's like the walls are made of oiled up ice. Now the next thing I wanted to work on was some animation for the player movement, and I'm basically just replicating what I did in the old game. Now while some of the animations are frame-based, such as the gun reload and the ball spawning, the player walk animation is just based on a sine wave, the components of which are some position offset, rotation, and some squash and stretch. This is the result of those elements combined, which is going at a quarter speed for clarity, and here it is in real-time speed, and implemented into the game. Now let's talk a little bit about game audio. Godot is a very modular game engine, so instead of having a separate thing to handle sounds, it just has audio nodes that you can add anywhere in the hierarchy. So the old version of this game had these littered around wherever different sounds were needed. And this time I wanted to be more organized, so I made an entirely separate object for handling all audio, which could be called by other objects. This so-called audio player holds a dictionary of all the sound names and the corresponding sound files, and so an object that wants to play a sound just has to call a function and include the sound name as a parameter, after which the audio player will find it in the dictionary and play it. So now that the player's boots were finally making stomping sounds on the stone tiles of whatever the hell this room was anyway, it was time to add guns. And balls. The basic functionality of these two was pretty easy to add, since the behavior is pretty straightforward and the ball uses built-in functions for bouncing. When shot, the ball starts off in the active stage, where it bounces around and damages the players if hit. After a certain amount of bounces, it changes to the transition stage where it slows down to a stop, and then it changes to the idle stage where it can be picked up. In this stage, the ball checks for overlapping bodies that could pick it up, and because the ball handles the pickup detection, it needs to distinguish between things that can pick it up and things that can't. We don't want an overlapping wall to be able to pick the ball up after all. So how do we do that? The obvious way would be to detect if the overlapping body is a player, But this actually isn't very scalable, since if we add other types of bodies that can pick up balls, we have to define each one of them individually. So here's where one of my favorite programming concepts comes in: duck typing. Now, duck typing follows the ancient wisdom of if it walks like a duck and it quacks like a duck, it's a duck. And how this applies to programming is, instead of checking whether the thing is something, we check if it has something, which in this case is the function pickup_ball. So in essence, all the ball has to do is check if the overlapping body has the function to pick it up, and if so, to call that function, and then of course delete itself. Now, while the ball's wall collisions can be handled with built-in functions, that's not the case for hitting players. Because while the built-in collisions know when they've hit something, they don't actually know what they've hit, which is important when considering which player to damage. So player collisions have to be made from scratch. Not that scratch. So at first I added a system very similar to the picking up of the ball, where the ball checks for overlapping bodies every frame in the active stage, and if the body has a handle hit function, it calls that function and reacts accordingly. And as simple as that is, it just works. Sometimes. Most of the time it seems to go inside the player instead of bouncing off of it, and every now and then it seems to just go straight through without even hitting the player. To explain why this happens, here's a player and a ball that's going towards it. Everything you're seeing here consists of sprites, which are usually exclusively used for showing stuff to the player. These are the object's colliders, which are normally invisible, and they're used for hit detection. So this is everything the code actually cares about when handling collisions. Now the ball moves a certain distance every frame, and then checks for collision. And in this case, the ball happens to overlap the player during a frame. If the ball is sufficiently fast though, in some cases it might be on one side of the player in one frame and move to the other side in the next, while never actually registering a collision. Now if you're coding shooting into a game and want the easy life, replace the physical bullet with a ray cast, which can be pointed in a direction and will stop at the first thing it hits. This all happens in a single frame, so no more frame shenanigans. If you really want to use bullet objects, though, you're still going to be using raycasts, just invisible ones. Now most games will put a raycast between the bullet's previous and current positions to see if there's anything in between that should have been hit. This doesn't work for us though, since the ball has already gone past the player when it registers a hit, and we want the ball to bounce back off of the player. So instead of checking between the previous and current positions, we check between the current and the next, which just means pointing the ray to the direction of the ball's current speed. And now if we detect a player, or more accurately a body with the handle hit function, we do some maths to move the ball to the surface of the player and call the function, which results in perfect surface bounces every time and no more ball penetration. I also added the basics of ball spawning, in which we do a simple animation with some sounds, and then spawn the ball that's already in its idle state, ready to be picked up. Moving on to something that didn't exist in the old version of the game, I want to talk a little about frame rate independence, which sounds boring, but the big title card means it's important. So the old version of the game ran at a fixed 60 frames per second, which meant it would always stay at that exact frame rate regardless of the monitor's refresh rate. Now even though being able to play at higher refresh rates isn't incredibly important for a small indie game, this game does have a competitive aspect, which means better frame rates are often beneficial. And since higher refresh rate monitors are becoming more and more popular, I at least wanted to have the option. Now, if we simply unlock the frame rate, meaning we let it choose the display's frame rate instead of forcing it to always be 60, it'd work as expected at 60 frames per second, but slow down at lower frame rates and speed up at higher ones. And this happens because everything in the game is frame-based by default. The balls move a certain amount every frame, the animations wait a certain amount of frames between each image, and timers get reduced by 1 every frame. And so if we have double the frames every second, everything will just be happening twice as fast. So what we need is some way to tell how much real time has passed between every frame, and then scale everything based on that. And in Godot, there's a built-in variable called delta, which measures the amount of seconds between this frame and the last one. So at 60 frames per second, the delta should be 1 over 60, aka 0.01666 continues. Now let's say we multiply this delta by 60 no matter what the frame rate is. At 60 frames per second, it should of course be 1. At, for example, 30 frames per second, it'll be 2, and at 120 frames per second, it'll be 0.5. We can actually incorporate this number into everything frame-based to make it frame rate independent. For example, if we multiply the amount the player or the ball moves each frame by this number, it'll always go at the same speed. If we divide the amount of frames between each animation step by this number, something that takes 4 frames at 60 frames per second will take 2 at 30 and 8 at 120, meaning it goes at the same speed. Some things are more difficult than others. For example, the length of the ball's trail adds a point at the ball's position every frame and stores it in a list. Now before, we could just remove the oldest point if the list was above a certain length, but now we have to store every delta time corresponding to a point and remove the last point if the sum of all the deltas exceeds a certain amount. And I'm sure there are things that I've so far forgotten to make frame rate independent, so the journey continues. And with that, here's some fun things I did while trying to figure out the serious coding stuff. A lot of this will probably be making its way over to the Chaos game mode, which is like the cooler cousin of the normal mode, and I'm probably gonna talk more about that in the next video, so stay tuned for that, but don't hold your breath because you might die. If you enjoyed the video, well that's good enough for me, and as always, remember to empty your recycle bin. Now get the f*** out of my house.